The topic of this presentation is using optical resonance in practical applications of electronic systems. This presentation is for Electronics 2, Winter 2017 at Oregon Tech. My name is Kelsey Lambach, and I hope you enjoy my presentation. Optical resonance is a phenomenon that occurs when photons are trapped in a standing wave pattern within a system. It is typically achieved using mirrors, but other reflective surfaces can also create this phenomenon. The reflection and use of resonance in a system is known as an optical cavity. Another name for an optical cavity is an optical resonator. This is the origin point of any system that will use optical resonance to perform a task. How does it work? Optical resonators are, as I said, formed when a series of reflective surfaces trap light. There are three main types of optical resonators: linear resonators, waveguide resonators, and ring resonators. These all have similar properties and use the same concepts and physical reactions within the three systems. However, there are slight differences in the way they are set up. The first is a linear resonator. These are the simplest resonators. They use a mirror system that literally makes linear lines to trap light, and it reflects back onto each surface, and it becomes a continuous loop. So these linear resonators are typically used in the formation of lasers or other systems where the direction of light must be channeled in a beam type orientation. Waveguide resonators channel light through a waveguide, so instead of reflecting light off of mirrors that you can see and it bounces back and forth, you use a spherical system where typically you think of like fiber optics, and it uses total internal reflectance to keep the light trapped within the system. So like in fiber optics, as I said, you channel the light through one end of the fiber, and typically fiber optics are either insulated or the material is such that the light doesn't leave it because of the reflectance properties of the material, and the light will go in one end and will reflect all the way down the sphere, the spherical or the cylindrical fiber, and will come out the end to produce whatever effect you're trying to accomplish. Now, ring resonators, they use two waveguides, as you can see in the picture. You can see it here and here, and then they use a circular waveguide here. And so the light comes in on one end, and it goes through, so it would come in here, and it would go all the way through the ring and come out here. The idea behind this is that it will help with latency of the system. So how fast data travels, it helps with modulating and other applications. They're not as well used as the other two, but they still do exist in IC systems and other various applications. So when we're talking about linear resonators, it's important to understand system stability. An optical resonance system is stable if the light rays remain within the system. It's unstable if the light rays stray from the system due to an alignment offset. So both of these are incredibly important when we're designing optical resonators. You can use stable and unstable systems perfectly effective depending on the application. So a stable system would require the light to remain trapped, and you would use those in systems where everything needs to remain contained, where you might have a high frequency of light, or you might have high voltage or what have you, and you don't want any of those rays to cause damage to a system. or an external system. You can also use them for increasing power, output power, and they have a lot less loss of power when you're trying to use them in a certain application. Unstable systems are effective if you are trying to direct light outside of the system, or you don't care about keeping everything trapped and contained. These systems can include anything that projects photons in, it can be random or controlled. So an unstable system could be, for example, something where you use linear resonance to reflect a bunch of light and then project it onto a surface or something along those lines. Now, what applications do these have? Linear resonators are used in lasers, biosensing, light modulation, data transfer, spectroscopy. There's a lot more applications, and it's a very hot topic of research right now in optical and electrosciences. So why does this research matter? This research matters because it's the cutting edge of technology right now. We have so many systems that are developing. We have biosensing, which allows us to use to detect various cells and abnormalities in the human body without having to do invasive procedures or put harmful chemicals within the body. Linear resonators are used in work with lasers, so anything that has to do with laser heating, laser cooling, metrology units, basically anything that has to do with the channeling of light. We also have IC integrated circuits. So integrated circuits in the optical world are becoming a new technology where data can be transferred extremely fast, a lot faster than regular electric circuits. And these systems allow us to make things a lot cheaper because there's a lot less power involved in optical systems than when you're just channeling direct electrons. And it's an incredible new, it's an old technology because I mean it, and everyone's known about optical resonators for a long time, but it's incredible to see how this old technology is being applied in so many new creative ways. And the applications between electro and optical engineering right now are rather cutting edge. A lot of this you can see it in as we were studying IC circuit design with the transistors. Well, we can remove transistors from the situation, which decreases cost, and we can also involve a lot more, as I said, cost-effective applications to create the same effect that we were looking at with more volatile systems. Optical resonance is the basis for practical applications of optical sciences and furthering research in the field. It is one of the forerunning bases for anything that has to do with the continuing of practical applications. I mean, I just said that, but the idea is that without optical resonance, we cannot continue the advancement of technology in our field. So I hope this presentation has helped you learn a little bit more about optical resonance. If you have any questions, feel free to contact me. And I hope that this shed a little bit of light on the field of optical sciences. So I thank you for your time and for listening, and I hope you have a great day. Thank you.